At this point, we have all the pieces we need to build a simulated CPU in Logisim. At the core of the CPU is the ALU that you're building for Homework 3. Our 8-bit ALU takes two 8-bit numbers as input and produces another 8-bit number as output. And it can perform any of 8 different operations as specified by the 3-bit opcode. But to turn this ALU into a processor, we need control circuitry that will let us store data and execute a program. And so in this video, we will be laying out the data path for the CPU. At a baseline, we need somewhere to store the data that is being given as input to the ALU. And so we can add two 8-bit registers to our canvas. And we'll label these registers A and B. And for now, we can connect the output of these registers to the inputs of the ALU. And then whatever we give as the opcode bits to the ALU will determine what operation we are performing on these inputs. The ALU will then produce the appropriate output, and we can loop that output back around to become the input to both of these registers. But in general, we don't want to store the result of every arithmetic operation into both of our data registers, and so we'll need to take advantage of the enable wires for these registers. Which register we want to store the data in will differ depending on what operation we are performing, and so we will need to have this enable bit determined by the control circuitry that you will be building as a part of the homework. And so we will, for now, connect these enable bits to a Logisim component known as a tunnel. Tunnels are found under wiring, and we'll make it face north. And the label for a tunnel is very important because if we have multiple tunnels on our circuit, they will be distinguished by their label. So I will label one tunnel A enable, and I will make another tunnel called B enable. And what a tunnel lets us do is analogous to having a component that tunnels into the circuit board, and then a wire is run inside of the board and comes out somewhere else to be fed into some other component. So this allows us to connect components that are on different parts of the canvas without having wires crisscrossing every which way. Let's zoom out a little to give ourselves some room to work with for setting up these control bits. Eventually, the enable bits for the A and B registers will be among the outputs of a finite state machine that you will be implementing in Homework 4. The job of that finite state machine is to control the state of the CPU as it is performing various operations. And so, among other things, it needs to control when the output of the ALU gets saved into various registers. The enable bits for the various registers will all be bundled together as a single output of the control unit. So we can add a splitter to the canvas that will let us tease apart from that bundle the bits for enabling the A register or the B register. And we can connect the other end of our tunnels to the outputs of this splitter. So now, if the finite state machine that you build outputs a bundle of enable wires, then we are splitting up that bundle and sending the A enable into this tunnel, where it will go through the circuit board and come out at the other end of this A enable tunnel, so that when this particular wire from the bundle carries the value 1, we will enable the A register and update the value that it's storing. The control unit will also be responsible for producing the opcode bits that control the operation that the ALU is performing. So we can add another tunnel, which we'll call S for ALU Select Bits. And this needs to be a bundle of 3 wires going into the select bits for the ALU. So I'll change the data bits to 3. And then I can put the other end of this tunnel. And this will be an additional output of the control unit finite state machine. At this point, let's add a circuit for this control unit. And we'll edit its appearance to be a large rectangle. And for the function of this control unit, we know so far that it needs one output, which is at least 2 bits wide, which is the bundle of write-enabled bits for the various registers. And we'll also need another output, which is 3 bits wide, which is the select bits for the ALU. Going back to the appearance, I'm going to move these around slightly. And now back on the canvas for our CPU data path, we can add our control unit as a subcomponent. And we can connect up these outputs to our tunnels. In order for this control unit to output the opcodes that control the ALU for the particular program that we are trying to run, we need somewhere in our circuit that we can load in the program that we are running and then give that information to the control circuitry so that it knows what instruction is currently going on. And the way that we will give a program to our simulated computer is by loading that program into the RAM. RAM stands for Random Access Memory, and it behaves a lot like the ROM component that we've already seen in our finite state machines, except that in principle we could also write data to the random access memory. In our case, we want 8-bit address inputs and 8-bit data outputs, so those defaults are fine, but we'll want to change the data interface to asynchronous. To make use of this RAM component, we'll need to give an 8-bit address as input, specifying the location in the RAM from which we want to read data, and then the RAM will produce as its output the 8 bits of data that were stored at that particular location in the memory. So we then need to get that data that is output by the RAM into a register in our CPU so that we can make use of that data. But since we only have these 2 data registers in our simple CPU, we don't want to be overwriting them every time we need to read an instruction from memory. And so instead, we'll add an additional register called the memory buffer register, whose job is just to take the data that came from the RAM and at appropriate times save that so that the rest of the CPU has access to it. We'll add another register, and we'll label it MBR for memory buffer register. And we'll again take advantage of a tunnel. The output of the RAM is an 8-bit bundle, so we'll make our tunnel have data bits equal to 8. And we will label our tunnel data. And then we'll make a copy of that tunnel facing the other direction and connect it as the input to the MBR. So the way this RAM component works in Logisim is that at all times it is outputting the data at whatever location is given by its address input. But the MBR is buffering that output from the RAM by only accepting that data as input and storing it when the enable for the MBR is turned on. And so we'll need another output from our control circuitry for the MBR enable. So we'll replace our splitter with a 3x3 version. And then in the control FSM, we'll need to make our write output have 3 data bits. So now the control unit also gets to say when are we enabling the memory buffer register, and therefore when are we accepting data into a CPU register from the output of the RAM. One of the most common cases where we will be loading data into the memory buffer register is when we are loading the next instruction of our program into the CPU, and in that case we'll want to send the instruction from the MBR to the control unit so that the FSM can update its state based on the instruction that we are trying to execute, and then produce appropriate opcodes and other outputs so that the CPU actually completes the instruction. But it turns out that 5 bits is sufficient to describe all of the instructions that we will be implementing in our CPU. These instructions, by the way, are the same ones from your assembler in Homework 1, and so programs written in terms of those instructions and then translated with your assembler will ultimately be possible to run on the CPU that we are building. And since we only need 5 bits to specify the operation that the CPU is performing, we actually don't want to send all 8 bits from the MBR into the control unit. Rather, we want to use a splitter, and for this splitter, I will give it a bit width in of 8 and a fan out of 1, and then I can choose which of the 8 input bits I want to be among the 5 output bits, and we want to leave out the last 3 so that only the 5 low order bits are passed as the output of this splitter. And now if I connect it to the 8-bit bundle coming out of the memory buffer register, then I can send just a 5-bit input into the control unit, and then the control unit doesn't have to worry about those extraneous 3 bits. So now we should update the control unit to take these 5 bits from the MBR as one of its inputs, and we'll edit the circuit's appearance to make sure it lines up nicely. And now back in the CPU, we have our MBR input coming from the 5 low order bits of the MBR. But sometimes the thing that we're loading from the RAM is not the next instruction of the program that we just want to feed into the control unit. Sometimes we'll actually be loading data into the MBR that is data that we want to use in our program. And so in that case, we want to send our data into one of the data registers. And we could do that by connecting a wire around and having this also be a possible input to each of our data registers, and then we would need a multiplexer that chooses among the possible inputs to the registers. But a better plan is to take advantage of the fact that one of the operations our ALU can perform is to just pass along one of its inputs as its output, and then use the fact that the ALU's output is already connected into both of our data registers. So that means that we can just have a single multiplexer on the B input to our ALU, and this multiplexer will select between the B register and other possibilities as this input to the ALU, which we can, when we want, then just pass back along and enable one of the data registers. So the advantage here is that we don't need to have a separate multiplexer on each of our registers, and we can get away with just a single multiplexer on our input to the ALU. These data lines are all 8-bit bundles, so I need to change the data bits to 8. And as always, I will turn off the multiplexer's enable bit. And right now, we only have 2 things that we are selecting between, but we're eventually going to have a few more possibilities that we might want to give as input B to the ALU, so I'm actually going to set the select bits here to 2. And I'll connect register B as the top input to this multiplexer and the MBR as the second input. The other inputs to this multiplexer will be one more register that we'll talk about in a moment and a user input to the CPU. So let's add that user input now. We can add an input to the whole CPU circuit and give it 8 data bits, and then connect that up to the bottom input of this multiplexer. And this gives us a way to give data input to the CPU that's not part of the program that we write and assemble in advance. And this corresponds to the input instruction in our simple programming language. So when the instruction is 00100, that should be the case where the control circuitry causes the data in the input register to be passed into one of the data registers. So now that we have this multiplexer that's choosing among several possibilities for the B input to the ALU, we need to produce the select bits for this multiplexer as one of the outputs of our control unit. And so again, I'll add another tunnel, and we'll call this the B select, because this will be how we are selecting what becomes the B input to the ALU. And our data bits need to be 2. And now I'll put a west-facing copy up here as one of the outputs from the control unit. And on the control unit, we will add an additional 2-bit output, which we will call B select. And so now among the tasks of our control unit will be to output the 2 bits that determine which of these possibilities becomes the B input to the ALU. So I mentioned that we were going to need another register, and let's add that now. And I'll call this register PC, which stands for Program Counter. The job of the program counter is to always store the index of the next instruction we will be executing in our program. And in our simple CPU, we will always load programs into the RAM such that the first instruction of the program is located at address 0 in the memory. And so if the program counter starts with the value 0, then we can use the program counter to tell us what address do we want to load the instruction from, and then we can get the first instruction of the program from the RAM, and we can increment the program counter to now point to the next instruction that we will move on to after we have executed the first. And so that means that the primary way that we need to connect up the program counter is as the address input to the RAM. But then we also want the program counter to be one of the things that we can input to the ALU, because an operation that we will frequently want to perform is to increment the program counter. Once we have loaded instruction 0 from the RAM into the MBR and started executing instruction 0, we'll want to increment the program counter so that it now has the address 1, and we can, when we're ready for it, load the data at address 1 so that we can get the next instruction in our program. And so because we will often need to update the value in the program counter by incrementing it, we will want to have the output of the ALU connected into the program counter so that we can store that incremented value we've just computed back into the PC register. And once again, we'll need an enable bit that tells this register when to store a value versus when to ignore the data that's coming out of the ALU. And now we need our control circuitry to also output a PC enable bit. So I will change this splitter to be 4x4 and connect up to the PC enable and edit the control circuitry to make this a 4-bit output. And so now we have the ability to store values into the program counter, either based on incrementing the previous program counter, or in the event of a jump instruction, we could store a value that we have loaded from the memory into the program counter by loading the data from the memory into the MBR, and then passing that through the ALU and storing it into the program counter. We now have most of the Datapath components of our CPU on the canvas, but for our CPU to actually run, we're going to need to give it a clock signal. We will add one global clock signal to our CPU canvas, and then we will give that clock signal as input to the various components that need to be synchronized by the clock cycle. That includes all of the registers, as well as the control unit finite state machine. So to simplify this, we'll send our clock signal straight into a tunnel, and we'll label that tunnel CLK, and then we can have that clock signal given as input to all of the various registers. And we can also give the clock as an input to the control circuit. We'll need to add one more input pin. And in addition, when we are testing our CPU, it's going to be really convenient to have the ability to set it back to its initial state after we have ticked through several clock cycles of execution. So we will add an input pin, which we will use to reset all of the registers and the finite state machine. I'll label this pin RST. And again, I'll send it into a tunnel, which I will also call RST. And then we can send that reset signal into the various registers. On a register, this bottom right input is the clear pin. And we'll also give the reset as one of the inputs to the control circuitry so that the finite state machine can go back to state 0 in the event of a reset. And so we'll need to add a reset pin as input here, and make sure it appears in an appropriate place. And now we can connect it to our tunnel. So now when you are testing your CPU, if you ever want to go back to the initial state, all you need to do is toggle the reset, and that will send a clear signal to all of these registers. And you should likewise set up the registers inside of the control FSM to take the reset signal as an input on their clear pin, so that whenever we toggle this on, all of the registers go back to their initial state, and then we can turn it off and start simulating our program again. There are just a few more things that we need to do to finish up our data path. One of them is that we want our control unit, when the program reaches a halt state, to let us know that by outputting a halt flag. So we will go back to our control unit and give it one more 1-bit output, which we will call halt. And then we'll edit the appearance to put that halt pin at the top. And then back on the CPU canvas, we will connect that up to an output pin for the whole CPU. And so we will be able to see when our program completes by this halt pin going from 0 to 1. And the last thing that we want is the ability for our CPU to produce some output. So let's add one more register that the CPU can write to in order to produce output. And we can make it writable by connecting it to the ALU output. And then we need to give it an enable, and we'll call this tunnel out enable. And so now we need another output from the control unit to govern the enable bit of the output register. We'll change this to a 5x5 splitter. And one last time, we'll go back to our control unit and change the write data bits to 5. And then we'd like this out register to actually display the value as an output. And so we can do that in a couple of different ways, one of which is to add an output pin. And this will be helpful for automatically testing the circuit. So let's change the data bits to 8. And we can now see this output in binary. But it would be nice to not just view this in binary, but also to view it in hex, because that's much more readable. And in Logisim, we can choose the output component called a Hex Display. And with 2 hex digits, we can display 8 binary digits. And so now we can use a splitter facing north, switching its handedness. And now we will connect this to our output line. Our fan out will still be 2, but our bit width in will be 8. And now we can connect the high order bits to the first digit and the low order bits to the second digit. And now we have a hexadecimal readout of whatever value is currently being stored in the output register. So this is the layout of our simulated CPU. We are using the ALU to perform various operations, but which operation we are performing and which data is being given as input to that operation is governed by the control unit that you will implement in Homework 4. Part of that implementation will be figuring out when do we want each of the different registers to be enabled to store the output of the ALU or the output of the memory. And also, when do we want to send which input and which opcode into the ALU. So your main task on Homework 4 will be to break down each of the instructions in our programming language into the steps that the CPU needs to perform in order to execute that instruction. And then you will need to set up your finite state machine so that for each of the instructions, it appropriately steps through the states that will cause the CPU to perform each of the parts of that instruction that you have identified. In the end, you will be able to write a program in terms of this instruction set, assemble it with your assembler code from Homework 1, and then load that assembled program into the RAM and run that program on your simulated CPU. In class, you'll get a chance to set up the circuitry that forms the basis of the control unit finite state machine. And then on the homework, you will work out how to program the ROM of that finite state machine so that your CPU can carry out all of these instructions.